Okay. So we want to touch on in pumps. All right. Okay, so really quickly, this is becoming more and more popular, is spending a little extra, and rather than getting a pump that pumps a constant flow and a constant head, well, I guess it's not constant, but a pump that runs at one speed. And so it's constantly moving a certain amount of energy into the system, and you're controlling the flow rate with a valve. And the valve then is burning energy up. You put too much into the system, make sure they have the maximum, and when you don't need the maximum, you then are just sit and burn the energy. And you think about this, a system of a city that lives down the flat, and they may have a tank. This is why cities generally have elevated tanks. It's not because they try to store the water up in the air, it's so they can pump the water up, turn the pump off, and let gravity supply the flow. That way their pump's not always on. Well, with the advances in electronics, we've had these for a long time, variable speed pumps, variable frequency, variable speed. They use slightly different names, and there may be slight differences in them, but they all kind of mean the same thing. As we change the rotation of the pump, that way we change the flow in the head. So rather than adding additional energy and then controlling it with a valve, we're only going to put in the amount of flow that we need at the head that we need. And now we're saving power because the cost of electricity has went up, and so now it is worth it in many cases to have a pump controller that will do this. And in order to do this, we use what's called the affinity laws. All right? And these are listed in chapter 11. If you think back to fluids, when we talk about modeling, we can use the principles of modeling, and I'm not going to go through the derivation of all this, but this does come from those principles of modeling, and typically, so affinity laws. Okay. And this, pump manufacturers would use these when they would design a pump. They would size a pump, say, okay, I'm going to build a pump with a 12-inch impeller. And now I want to model it down to an 8-inch impeller. How's it going to perform? And I can test it in the lab, and then I can scale it down to how it's, so I don't have to test every single size of pump. Change the rotational speed of a pump. So without going into the modeling side of designing pumps, let's talk about the rotational speed. So this is useful when pump rotational speed changes. Okay, so we change the rotation of the motor. And these simple relationships is, we're going to let the pump rotational speed, sorry, I should have put this up here, we're going to call that N, which is the same value we used when we did specific speed. We did the little problem specific speed. So N has units of RPM, revolutions per minute. Okay. Now, typically pumps have, or motors, because the motor determines the speed, but motors have some set speeds. 1700 or 1750 is kind of a standard one. 900 is another one, or 3450 is another one. Okay, and these are kind of industry standards of when we size these motors, they're going to rotate at that. But if we can change the rotational speed, we can then change the performance of the pump. So using the what's called the affinity laws, we can now come up with the following criteria: that the rotation of pump, or the flow rate of pump, I didn't say that right. If I'm rotating at a certain speed, a certain N value, I get a certain flow rate Q. So Q sub 1 is correlated to N sub 1. So let me put this over here. So Q sub 1 is tied to a rotation of N sub 1, and Q sub 2 then is tied to a rotation of N sub 2. And these are also going to be then tied to some differential heads, H sub 1 and H sub 2. So these affinity laws tell me that the ratio of Q sub 1 to Q sub 2 is a function of N sub 1 over N sub 2. So it's almost like a simple linear relationship. If I cut the rotational speed in half, I cut the flow rate in half. Okay? And that's kind of nice for flow rate, but flow rate's the only one that's linear like that. If I look at head, then head boils down to that the relationship or the ratio H sub 1 over H sub 2 is equal to N sub 1 over N sub 2 squared. So if I cut the rotational speed by half, I cut the head down to 25% of what it originally was. Because 1/2 squared is 1/4. So my ratio of my head is 1/4, right? Or if I speed my motor up, I talk like we're always cutting the motors back, but sometimes we can speed things up. Now, a little word of caution here. The more you speed a motor up greater than it's designed for, or let me just say this, the faster a motor goes, the maintenance on the pump is raised to the 4th power. It's not a linear increase. You actually put more wear and tear on your motor, I think, raised to the 4th power, 4 times as much, which is not the 4th power, but I think it is 4 times as much by the rotation. And then we have one other similarity law is power. We want to know how the power changes. And we say P sub 1 over P sub 2 is equal to the cubed ratio of the rotational speeds. Oops, not squared, cubed. Okay. Now, I would note that this makes the assumption that we stay within the same efficiency curve for power, which is not always the case. So power, it works pretty good, but you may be off anywhere from 3 to 5% on the efficiency. But the head and the flow are spot on. So you could actually recalculate the power, and then you'd have to just find a new efficiency off of your pump, okay? Are we out of time? Oh, pretty much out of time, okay. So on Wednesday, we'll go ahead and take these relationships and just kind of set up where we're going here. We will take these relationships and we will plot them, and we'll come up with new pump curves. We'll keep the same system curve because the system curve doesn't care what kind of pump you have in it because it performs the same. So we'll come up with a new pump curve and find out where that pump curve is operating at. And that's how we can now figure out how things vary if we change the rotational speed and use a variable drive pump in our system. Okay. Now you do have a homework that's due tomorrow. Okay. We can go ahead and push that back to Wednesday because since I'm not going to have, we haven't went far enough along for me to assign you a new one. So the homework on pumps in parallel and pumps in series that I assigned before the exam will be due on Wednesday. All right. Have a great day. We'll see you on Wednesday.